Toast, toast. William, Jair, can y'all hear me okay?
Yeah, I can hear you.
Okay, all right. We haven't started. We'll get going here in a few minutes. Yeah.
So this is technically right, so, right?
Yes, it is technically red. It's correct. Yeah, because yeah, let me see. I'm trying to remember. Yeah, because all you did was replace theta with what theta was. Yeah,
Because
that's
I knew you showed us the other
yeah.
day, which is
Mhm.
what that was.
Yeah.
On the test, I was like,
Yeah. No, it'll work. Yeah, I couldn't say it's wrong, right? It's not wrong.
one of those things that is like hoping it worked out.
Yeah, yeah. Hey, tests are over in that corner if you want to pick them up. If you feel like you're too close, you can want to slide that back, you can. Okay, 9 o'clock. Welcome back, everyone. Hope you had a great weekend. So exam 2. The results are here, and everything in blue is exam 1, and orange is exam 2. The class average was a 45. I've only looked at what you did in class, okay? What you sent me, the next day or whatever. Haven't even looked at those. I've been doing other things. So this is as of right now, if I were to just go off of what was done in class. So and then also, I think I sent out an email that we have to send out updates, midterm grades and stuff. So that was based off of this. So almost the whole class was sent something saying, you know, hey, you're not passing, blah, blah, blah. So I was hoping that would kind of shake you a little bit and kind of scare you a little bit. Yeah, 13 people did not pass the test. And everybody's grade went down from exam 1. So I was talking to some students before all of you got here. And the big question was, you know, can I recover from this? I'm still trying to figure out what went wrong. Is this COVID? Was the test too long? I said, I do not believe that the problems were too hard. I think they were all within reason from what we've been doing or what you were doing on homework. So with that said, everyone will have the opportunity to make this better. I'm not sure exactly how we'll do it. In the past, what I've done is I've said, okay, if you had a low test score, your final exam can replace that lowest score, completely replace it. Now, I mean, that's good, right? Because that gives you an opportunity to bring this score up. The bad news of the final exam is a 3-hour test, and it's 3 hours? Yeah, 2 hours, 40 minutes, something like that. And it's going to cover almost entirely chapter 8, which is sequences and series. So even though this material won't be on the final, you're still going, the material that's going to be there is going to be just as difficult, if not more difficult than this. So, you know, there's kind of a catch there with it, I guess. So what I hope to see is the next test, some improvement from this. And then hopefully with the exam, you know, it'll be better than this score. So it'll be hard to say at this point, like what you need on the final to get an A or to get a B. But I would just say that this in your mind can be just a bad day. Okay. All right. So the test that you did at home, I'm going to have to figure out how I'm going to factor that in, because if I grade those and somehow adjust this score, then your final can't replace this test. You know, I've got to see like what works out better for you. And I honestly am not looking forward to grading all the exams again. I don't like to have to do it twice, but it was more of an exercise for you to go home and see like what you didn't see in class. Are there any questions on this? Grades, or just kind of like where we go from here? I mean, don't be too bummed out. I mean, I've told you already, like you probably learned a ton getting ready for this test, and you probably learned more about yourself after the test, you know, like, you know, it's hard class. So yeah, you have to, I mean, you have nothing to lose. You got to go for it at this point, right? But make adjustments. I know some of you did study groups, and I know it's disappointing when you work so hard and then you get a result like this. I know that's discouraging, but you have to keep at it, you know? And maybe that study groups need to be like more consistent, you know, like every weekend instead of just the weekend before the test. I don't know. Do what you need to do. Okay. One last thing, the problem recognition, right? You get to the test, you look at it, you're like, oh, what do I do? That comes with practice. I mean, it just, you have to be doing so much of this that it just becomes like, yeah, I see it, you know? And I don't know, it's hard. It's hard. So, okay. All right, that's all I have to say about grades, unless there's anything else you want to add.
UTSA library is open 24/7 Monday through Thursday.
UTSA library is open 24/7 Monday through Thursday. Okay.
Friday and Saturday close at 9.
How's the parking there? Do you have to have a permit?
Yeah, you do
Uh-huh.
park in the open area at your own risk.
Okay.
Park under the parking garage. It's like every 2 hours, $5.
Okay. Okay, so there's some paid parking. You can try and park if you want, but be careful. You might get a ticket.
Caves in the garage on weekdays,
Yeah.
and then Saturday, Sunday, it's full.
Are they open, the library open on the weekends?
Yes.
I thought you said Monday. Oh, Monday through Thursday, 24/7. On the weekends, other hours?
Saturday they close at 9.
Mm-hmm. I've got some Cal 2 students that are my online students that are doing public library, because public libraries have rooms and whiteboards. I just know that their hours are a little different, but they're open on the weekends. So, and it's free. I think you do have to make a reservation. Just go to like, Google San Antonio Public Library, and then you can find what locations and, yeah, yeah. Okay.
Yeah. I'm a student too, so I'm able to get the study rooms if y'all just want to get a study room, just like
Yeah.
I'll book y'all.
Back before I was married and had kids and family, I used to meet my students at in their study sessions on the weekends. That was cool because we could, I had nothing else to do but to do more math. So it's fun. It's fun. But, or we would even come on campus here, just open up a room here. We'd spend hours on the weekends. All right, so yeah, if you do study groups, you can let me know. I wouldn't mind. I think some of y'all texted me during their meeting and needed help or something. Y'all feel free to reach out if you have something. Okay, let's get down to what's new for today. So we are going to start 7.2, which is going to be volumes. Now 7.1, I know this was like before the test, so you may have like cleared your mind of this, but what we were doing in 7.1 was finding the area between two curves, right? And there is a pretty simple formula for 7.1. Let me bring up our notes here. So for 7.1, what we discovered or what we taught, whoa, hold on. My pen is going to the wrong screen. Hold on just a second. All right, I've got problems. Okay, I have to unplug this and plug it back in. There we go. Hang tight, technology, right? There we go. All right, so in 7.1, it was areas between curves. And there were like two main concepts, I guess, here. One concept was how do you find the area between two curves? And there was just a real simple formula. But the other main concept was this idea that we can now look at functions that weren't functions of x, but functions of y. So those were like the two main ideas. So if you had, let's say, two functions of x, let's say that this is f and this is g, and you want to find this area between them, then we imagine that there, well, not imagine, we visualize these infinite number of rectangles that we draw on here, right? And so that area would become the integral from a to b of the top function, which in this case would be the f function, right? So it'd be, I'm just going to write top, okay? And then you subtract from that the bottom function. And this will be with respect to x, dx, because our rectangles are vertical. And then our limits of integration go from a to b are the two endpoints. Now, those might be where the two functions intersect. The problem might state that there's vertical lines. It just depends. But the general idea was top minus bottom, right? Integral from a to b with respect to x. And that's what we do when we have functions of x. And then the other one was if we had functions of y. So now your functions do this. This would be some f of y. And then you'd have something like this, which would be some function g of y. Then we have to use horizontal rectangles instead. And then our formula becomes a little different. We go from C to D instead of A to B. And instead of saying like top minus bottom, we would say right minus left. So this would be the function on the right minus the function on the left. And we'd be doing this with respect to y. And I also said one more thing to you, which you may have forgotten, and that is when you think about these rectangles and where they are within that region, you have to imagine that the rectangle is going to be sliding from left to right here. And then from here, it's going to go from the bottom to the top, right? These rectangles move through. And so at any given point, if I were to isolate just one of these rectangles, like this one in blue, I said that the distance from the origin to that rectangle right there, do you remember what I told you that value would be? No, f of x is the height, right? The distance from the origin to the rectangle will be x. And so when you think about this integral going from a to b, what you're really doing is you're saying, I'm going to start this rectangle out on the left-hand side, which means I'm going to start at a, so x will be a. And then as I move across, the rectangle moves across, right? They move across, your x is going to range from a to b. On this picture, the distance we're talking about is the distance from here to here. That's a distance from the x-axis to the rectangle. And what do you think that would be here? Y, okay? Now, again, I told you that last time just to kind of get it in your mind because we're going to need it here soon, all right? So here, the distance from the x-axis to the rectangle here is y, and y will vary between c and d. Here, the distance from the y-axis to the rectangle is x, and x will range between a and b. All right, that's 7.1. All right, we're done with that. We're going to start 7.2 today. So let's talk 7.2. I need to bring this up over here. Here we go. All right. So we need to get through some preliminary things. At home, everyone's good. You can hear me. You can see the screen. Everything's, you're happy? Yeah. Okay. All right. So some preliminary things that we need before we can even begin this section. The section is called volumes, right? So when we think about volumes, that's something three-dimensional, usually, right? You're talking about something three-dimensional. If you're talking about something on a flat sheet of paper, that would be an area. And then one-dimensional would be just a straight line or a curve which would have a length to it. So here we're talking volume. So we need to know some volume formulas from the past. The first is if we have a rectangular box, which in mathematical terms is called a parallelepiped, that's a box, okay? Then if you take this three-dimensional box here and you want to know its volume, then you just do length times width times height. So I think that's something we've all kind of seen in the past, right? I don't need to discuss that anymore, right? Length times width times height, okay. Hold on, I'm waiting for one more program to open here. There it is. Okay, and then the volume of a right cylinder. So this is a cylinder. Now notice, normally when we do cylinders, right? When we draw a cylinder, we usually draw a cylinder like this. It looks kind of like a beer can, right? I've drawn it really flat, right? Really short, but there's a reason for that, all right? But it's the same as this picture. And it's just, this is a little taller. So we say that the distance from here to here, that distance right there we call h, which over here on this one would be this, h. If that's h, the height of the right cylinder, and r is the radius, which goes from here to here, and in this picture, it would be this right here, then the volume of this is pi r squared times h. You should recognize pi r squared as being the area of a circle. So essentially, all you're doing here is you're taking the area of the circle and multiplying it times how tall it is. So it's like you're getting that area, and then you're kind of multiplying it to get through the depth of it, and that'll give you your volume. Is that clear? Y'all have seen those formulas before? We're all okay? Okay, Wrong button. Okay, now, the next thing that we need to kind of think about is what would the volume of this be? Okay, so let's say we were given this thing that we will call a washer. So if you're given something that looks like this, let me make this a little bit bigger. So if we're given something like this, if we have the center here, let me change my color. There we go. So if we have our center here, we have an inner radius, call that R in. That's the radius of the inside, right? And then you have an outer radius, which goes from here to the outer edge, call that R out. Then the formula for the volume of this, I have written here. But I want us to just think about how we get this formula. So it's a pretty simple idea if you think about it. All we have to do is first figure out the volume of the big one, right? And then subtract from that the volume of the small one, right? If we do that, then we'd have the volume of the washer. So the volume of the big one is pi times the outer radius squared h, because that would give us, I mean, that's the cylinder formula, right? So that gives us the volume of the big one. And then we subtract from that the volume of the smaller one, which just uses the inner radius instead of the outer radius. Subtract the two, and that would be our volume. And then on this, you can factor out a pi. I factored the pi out from the front, right? And then I factored out the h, but I put it on the back side. Now, I did that for a reason. You'll see why. I could have put pi h out front and then r out squared minus r in squared. But are there any questions on that formula? Does it make sense to you? Okay, this is just kind of basic geometry. So I don't think there's really any issues students have with this. Any questions at home? All right. Now, we're going to move on. All right, so here's the idea, all right? It took me about 2 hours to get this code written up to work properly this morning, or yesterday. I was trying to do this last night during the baseball game. So we have a picture here, right? This actually is just the sine function. It's just the first arc of the sine function, okay? So right now, if I asked us to find the area underneath that curve, right? Let me say this is the function f of x equals sine of x. And in fact, we would know that this starts at 0 and here's pi, right? Because that's where it goes through half of its period. So 0 to pi, here's sine x. If we were asked to find the area of this, right? The area, what we would do is, so if we want the area, it would just be the integral from 0 to pi, right? And then we would do the top minus the bottom. So you see with this rectangle, let me make the rectangle a little bit more narrow here. So with this rectangle, we can imagine that rectangle can be anywhere in here, right? Anywhere we want. Well, actually, it's going to start at 0 and then move across. But when we're trying to visualize what's happening, we just say, take some arbitrary rectangle in here, let's say there. And again, I'll point this out, even though it's actually not necessary for this. That would be x, right? The distance from the y-axis to here is x. We're just going to take the top function, which is the sine function, right? That's the top one. And we're going to subtract the bottom function. The bottom function is actually y equals 0, right? The x-axis. So you do the top minus the bottom, which is just sine x. dx, because we're doing vertical rectangles. And then we do that and we're done, right? That will give us the area of this thing. That is not at all what we're about to talk about, all right? What we want to know now is what would the volume of this be? Volume, what are you talking about, right? There's no volume here. What would the volume be if you took this graph and you rotated it around the x-axis? So right now it's a flat sheet of paper, right? But imagine bringing that flat sheet of paper kind of out into three-dimensional space, taking that sine function and wrapping it around the x-axis. You would get some solid, wouldn't you? What's the volume of that? So let me show it to you first, okay? Imagine this is now in three-dimensional space, right? Not a flat sheet of paper anymore. And we're going to take this and we're going to rotate it around the x-axis. And when we do that, we get this, right? I would like to know what the volume of that is. Now that seems like a very difficult question at first, right? How do you find the volume of something like that? But we're going to do this exactly the way we did this with the area. With the area, we did a bunch of rectangles, right? We said if we can find a formula for one of the rectangles, then we can use the integral to add them all up, right? And we just go and just slide the rectangles across. Same concept, but we have to do this rotation, right? Which is weird. So here's what we're going to do. It's actually pretty brilliant. We're going to go back to this picture. Let me move this. I'm going to just move the rectangle over a little bit, put it about right there. Okay, so what I'm going to ask us to consider is that rectangle right there. What if we just take just that rectangle and wrap it around the x-axis? Just the rectangle, we would get something like this. This is what took me 2 hours to get my code to do right here, this piece right here. If we wrap just the rectangle around there, we would get this, wouldn't we? And that is right cylinder, just sideways, right? And we know the volume of a right cylinder, it's pi r squared h, yes? So if I could come up with a formula for just this one little sliver, a formula for it, then I can use the integral to add them all up. But I need a formula that represents that one sliver. And we have to remember that as you move across, right, the sliver's changing, right? It changes as you move. It's bigger in the middle, it's smaller on the edges, right? When you get all the way to the edge, it's almost, well, practically nothing down here. You can't even really see it. It's down there, but okay. But it's the same concept, right? And that's why when I was trying to introduce the idea of area, I tried to make it very clear to you, hopefully I did, that when you look at this formula for area under a curve, that I didn't want you to look at it like, oh, f of x dx is just f of x dx. I wanted you to see that this was what and this was what? What was the f of x? The height of the rectangle, right? And the dx was the width of the rectangle. And so when you say f of x times dx, you're saying length times width or height times width, which is area. We need a formula that will not give us area, but will give us volume of that sliver. Understand? So let's talk about it. Maybe we can come up with it without even, let's move this back here so we can all see this. So I'll make it a little wider so it'll be easier for me to label. So if we take an arbitrary rectangle, okay, imagine we've got this arbitrary rectangle in there and we've spun it around the x-axis. Then what is the width? Let's start with that. That's normally the h, right? That's the height of the cylinder. But for us, it's the thickness of it. What is that for us? Dx, right? It's the same as the width of the rectangle. So that's dx, great, okay. And now what we need is the area of that circle. And we know area is pi r squared, right? So the area of that would be pi times the radius, I'm going to put in parentheses here, the radius squared, right? Pi r squared, but what's the radius? F of x. Because just like f of x was the height of the rectangle, now f of x is the radius of the cylinder. So this is just f of x. And so if you want to know the volume of this thing, it's just going to be pi times the function squared dx. So when I put the formula earlier, remember I told you I wrote it as pi and then radius squared and I put the h in the back? The reason I did that is because I wanted to do it here. It doesn't matter where you put that height. So this is it, pi function squared dx. That's it. That is the volume of one little sliver. And now I need to add them up. So I bring the integral in. Now, what are my limits of integration? In this particular example, from 0 to pi. Okay, and that would be it. So we should have an integral. It looks like this, the volume of the whole thing. Okay, please keep in mind, this volume right here is the volume of one slice of this, okay? It's the volume of one slice. If I want the volume of the whole thing, then I bring in the integral. I go from 0 to pi, and then I do pi times the function squared dx. That's it. That will give us the volume. Do you see now why it's so important to look at the integrand, the thing in the integral, to look at that and understand it? Because this really means we can, anything we ever need to add up an infinite number of them, as long as we can come up with a formula, we're in business, right? We're in business. All right. I don't want you to write that as like a general formula yet. Could we do this? Could we actually do this problem? Let's see, 0 to pi, pi, and then what's our function? Sine, so we could do sine squared x, right? dx, and you all know how to do sine squared, right? You can integrate sine squared. The pi can come out, right? And to do sine squared, we do the power reducing formula, right? So y'all want to do it? We can do it. Yeah, let's just do it. If you're just curious to know what would happen here, gonna have to clear the screen, if you don't mind. So if we were to do integral 0 to pi, let's pull the pi out. We've got sine squared. I'm going to go ahead and rewrite that as 1/2 1 minus cosine 2x dx. I'm using the power reducing for sine, right? So 1/2 integral 0 to pi of 1 minus. Does anyone have any questions where I'm getting any of this? You're okay? So this should be, oh, I forgot the pi out here in front. I pulled the 1/2 out, but I forgot to put the pi. 1/2 pi. Let's do the antiderivative. So the antiderivative of 1 is x, because we're integrating with respect to x. And the antiderivative of cosine 2x is minus 1/2 sine 2x. And we're evaluating this from 0 to pi. And so we plug pi in first. Okay, if we plug in pi, we get something, and then we plug in 0, and we get something. So if I plug pi in here, I get pi minus, okay, what sine of 2 pi? 0, right? 0, so that's all gone. And then when I plug 0 into this, I get 0 minus sine of 0 is also 0. So this is all 0. So this whole thing is gone. And so all you're left with is this right here. 1/2 pi squared, pi times pi. That is the volume. That is the volume of the solid generated when you rotate the function sine x around the x-axis between 0 and pi. Your volume is 1 pi squared, or 1/2 pi squared. That's pretty cool, huh? So I want to kind of show you this whole idea again, just kind of to try and convince you again that this works. I showed you one slice here, right? But really the idea is that you would have an infinite number of slices in here, right? So as you start to add more and more slices, right? More and more slices, more and more slices, as the width of all of those little rectangles starts to go to 0, right? You start to get this. I need to kind of get this out of here. This one's in the way, right? You start to get, hold on. I went too small. There we go. That should fix it. Kind of did something my computer program didn't like. I think I did a division by 0 in there. Okay. Did not like that. Okay. Oh, let me see if I can get this. There we go. Okay, it caught up. All right, so here we go. All right. So in the limit, right? In the limit, when the width of those rectangles goes to 0, you get an infinite number of rectangles, which means you have an infinite number of slices. And so it will essentially give you that picture right there. Okay. And now that we have this, I mean, this general idea, we can kind of blow the doors off it and do anything we want, right? For example, what if we wanted to look at the area between two functions and wrap that around the x-axis, right? Well, again, three-dimensionally speaking, all we have to do is take this region and wrap it around the x-axis like this, right? And we get this really cool shape, right? And what we want to know is its volume. And I'm going to make a little transparent so you can see that on the inside, this hole that goes through the center is not just a straight hole because it was dictated by the inside graph. You see that? So we've got this really strange shape on the inside too. So can we come up with a formula for this? Yeah, we should. As long as we can come up with a formula for one of the slices, the integral will add them up. So this is where we get to this idea right here. I'm going to do this by hand. I always put this note up, but I always wind up wanting to do it by hand. So what I'm trying to develop right now is a general formula. All right. This will work whether or not we're trying to do the region between two functions or just from one function down to the ground, just like the sine we just did. So if we start off with an XY axis here, right? This is X, this is Y. And then we have two functions. Let's just put one on top like that. We'll call that F. And we'll put one on the bottom like this, G. And we want to wrap this, rotate it around the X axis. Rotate about the X axis. Now, right, just so you know, like where we're headed with this. Right now, we're rotating around the X axis, but what's stopping us from going around the Y? Or why not rotate it around like any line? Why does it have to be the X axis? So we're gonna go even further out than this in a minute, but we got to get this down first. So we're rotating this region about the X axis. So I'm going to start by drawing a rectangle, the thing that I want to wrap around, right? So here's my general arbitrary rectangle. Now, here's the way I like to do this. I like to take everything and just look at it to the side. So over here on the side, I'm going to draw my x-axis, okay? Which happens to also be my axis of rotation, which I'm going to draw that in a dotted green, although it's hard to see green. And then I like to draw a little like circular arrow here that shows that I'm rotating about that axis, all right? Now, what is it I'm rotating? I'm going to bring this rectangle straight over. I'm rotating just this rectangle around, okay? So that thing's going to get wrapped around like this. And when we wrap it, do you all see what we get? A washer, right? We called it a washer earlier. Now it'll be vertical, right? It's going to be this picture here, like this. It's this picture, right? But let me see if I can turn this around. Come on, work with me here. It'll be kind of like that, right? Sorry, that doesn't look great, but get the idea. It's this way, right? Wrapped vertically. So we're going to get something like that. So you can try and draw this if you'd like. I'm going to just draw it. I'm going to draw it below it down here just to get a general idea of what it looks like. It's going to go like this. It's going to have some thickness to it. And it's going to have a hole in the middle. Okay, all that's important is that we understand it's a washer, right? It's a washer. So what is important to us in this washer? We need to know how thick it is, right? Well, we know that already, right? The thickness is dx, okay? So the thickness of this is dx. The rest of it is that formula, right? we talked about this formula a second ago. It's pi times the outer radius squared minus the inner radius squared, right? And then the h was our thickness. So we need to figure out what's the outer radius and what's the inner radius. Well, the outer radius, okay, if we look at this washer, the outer radius goes from here to that top edge there, right? But that is also the distance on my picture from here to here. This is my R out. Do y'all see that? The top edge of the rectangle is also the outer edge of the washer. So that distance from the axis of rotation to that top edge is my outer radius. And then the inner radius is the distance from the x-axis to the bottom edge. And we actually know what dictates those, right? The outer edge is dictated by that blue function, and the inner edge is dictated by the red function, right? So do we know the blue function? Yeah, it's f, right? So this right here, this distance is f of x for this particular problem. And this distance from here to here is g of x, right? The inner radius is just the g function, and the outer radius is just the f function. So that means that the volume of this slice, the volume of this should be pi times the outer radius squared minus the inner radius squared. I'm out of room. I need to move this a little bit. What am I missing in this formula? Dx. And that will give me the volume of just that one slice. If we want the volume of the whole thing, we have to add up all of them, which means we have to use the integral. So I need to know where to start, which this would be A, and here would be B. So y'all help me. What would this integral be for the total volume of this region that's between these two curves wrapped around the x-axis? What would it be? Integral A to B? Pi. So is it okay if I put pi on the outside? Just do it now. Okay. And then keep it in terms of R. We'll put F and G in there in a second. It would be R out squared minus R in squared dx. This is washers. Okay. This is called the method of washers. This formula here. As long as you can identify your outer radius and inner radius, you're in business. For this particular example, because of the way we drew it, this integral would become integral from A to B, pi out front. This would be f of x squared minus g of x squared dx. That would be it for this particular one. I would prefer that you try and not memorize this one, because f of x and g of x are not always your inner and outer radius, okay? Like I said, when we change our axis of rotation, things will be different. Are there any questions? Yes.
But this cylinder formula, where our height go?
Dx is the height,
Oh,
right? Because the cylinder is turned sideways. So how thick it is really how high it is. I mean, this is pretty, I mean, I don't know, man. I've been doing this for a long time. 20 years I've been teaching Cal 2, and every time I get to this, it still amazes me that it's actually this simple to come up with a volume of something rotated around an axis. So let's see, how blown away do we want to be today? Would y'all like to prove the formula for the volume of a sphere? We could do that, right? Think about how could we prove that the volume of a sphere, what is the volume of a sphere? 4/3 pi r cubed, right? That's the formula for a sphere. Now you could look it up, all right? But we have been told by somebody in the past or by a formula sheet somewhere. Our formula sheet has it, right? Look, I'll just show it to you. Our formula sheet has this. Yeah. Yeah.
So
we can use the integral, like let's say I have a hole, right?
Mhm.
It's all jagged, you can't really take it, it's a certain shape, right?
Yeah.
Not really. What if I want to fill it up with like concrete or something?
Mhm.
You would be able to take the integral and figure out the volume of it?
You would need to know about some of the jaggedness, though. I mean, you have to know how uniform is, because if you're talking about this volume here, like rotating, you would, okay, that,
Just asking.
yeah, I mean, you could, as long as you could, as long as it was symmetric, because when you rotate something around an axis, right, everything is symmetric around that axis. So as long as your hole, if your hole is like weird, but that's happening, you know, if you have that symmetry all the way around, yeah, then you should be able to, but you still need to know like how to draw that curve, right? So that you have a function. But we have ways of drawing curves. If you, there are computer programs where you put in the data, so you could like mark, you could like take different data points and then you could have it fit a curve to it. And so you'd have a pretty good idea. Yeah. Okay, so on your formula sheet, here it is. Hard to see it, but there you go. Come on, man, what's going on? Right there. For a sphere, the volume is 4/3 pi r cubed. Now, we're being a little ambitious here. Do we want this to be our first example? I don't mind. I mean, yeah, you want to go for it? All right. So we are now going to prove that the volume of a sphere is 4/3 pi r cubed. What do you think the best approach to this would be? What can you wrap around the x-axis and make a sphere out of?
Square root of r squared minus x squared.
Yeah, so a circle, right? Why don't we take a circle and wrap this a circle around the x-axis? Do y'all remember when we proved the area of a circle in here? We did. We proved that the area of a circle was pi r squared. Y'all remember doing that? We did do it. Okay. So we're basically going to take a circle. Okay. So hopefully we all are okay with the idea that if we have a circle of radius r, that the equation of that is x squared plus y squared is r squared. I know we did this. All right. Now, I'm not going to take the whole circle and wrap the whole circle around the x-axis because that's not a function, right? Fails the vertical line test and the horizontal line test. So it's not a function of x or y. But if we take this and solve it for y, we get square root of r squared minus x squared. And that actually just draws me the top half of the circle. And I could wrap that around the x-axis, couldn't I? And that would give me the sphere, wouldn't it? But I'm going to go even better than that. I'm not even going to look at that. I'm going to look at just the first quadrant of it. Because if I take just this and wrap that around the x-axis and then double that answer, that'll be the volume of a sphere. So we need to understand that this is the function y equals the square root of r squared minus x squared. And then what are our limits of integration? Where are we going to be starting and stopping here? 0 to little r, right? 0 to little r. So can you all see the rectangles in here? I have all these little rectangles. I'm going to come over here to the side. I'm going to draw that rectangle. I'm going to draw my x-axis, which also happens to be the axis of rotation. And then I have to look at, what is the outer radius? And then the inner radius, isn't it down there? Rn is the bottom of the rectangle, which is always just the x-axis, right? Which is always y equals 0 here. So using my formula, I don't know, are y'all ready for the integral? Do y'all see we can already put this integral together? The volume of the whole thing should be pi. Integral where to where? 0 little r, right? And then we're going to do outer radius squared. What's the outer radius Which one was the outer? Yeah, it was this thing, right? That's our outer radius. And our inner radius, isn't that just y equals 0? It's not, it's the ground. I mean, this couldn't be better, right? We're supposed to take the outer radius and square it. Take the outer radius and square it, and then subtract the inner radius squared, which is nothing, dx. If you go back in your notes, when we did the area, we didn't have this nice thing happen where we squared it. So we had to use trig sub to do it. Here, we're not even going to need trig sub, because when we square the square root, it goes away, and we get r squared minus x squared dx, right? The zero's gone. And now we can just do the antiderivative of each of these. Now remember, r is a constant, right? So what is the antiderivative of r squared? R squared x. So this is going to be r squared x minus antiderivative of x squared, which is 1/3 x cubed. And then we evaluate this from 0 to r. Questions? Where I've got any of this? Plug in r for x. So if we plug in r here, first thing we get here is pi. Let's see, if I plug in r there, I'm going to get r cubed, r squared times r, minus 1/3, and then r right here would give me r cubed. Okay, that's what I get when I plug in r. Then I subtract from that what I get when I plug in 0. And when you plug 0 in for x, what do you get? 0 kills everything off, right? So now I have pi, and then I have r to the third minus 1/3 r to the third, which is 2/3 r to the third. So if I clean that up, I can write 2/3 pi r cubed. 2/3 pi r cubed. What was the formula though? 4/3. But remember, we only did a half the circle, right? We had only rotated this. So if you rotate this around the x-axis, you're going to get something that looks like this, right? You're only getting half of it. So to get the answer, we just double it. So take that times 2. That gives you volume is 4/3 pi r cubed. If I would have told you this morning when you walked in that we would be able to prove that 4/3 pi r cubed is the formula for the volume of a sphere and that we would do it in under 5 minutes, you'd probably be skeptical, wouldn't you? Yeah, it's not that bad to prove that. But you have to understand, again, this integral is very powerful, very powerful. All right, any questions?
So this particular type of volume
Mm-hmm.
would be applicable for bridges that intersect different highways. Would not concrete is required for pillars that go up.
Yeah, I mean, anything you can think of that there's, the applications are pretty much anywhere you see solid objects that have some symmetry to them, right? Look, there's a formula. I usually give this as a bonus question to try and figure out if you can come up with the formula for the volume of a frustrum, which is basically this object here. So it has like a radius on top, R1, and a radius on the bottom, R2. And so, what's the volume of this thing? So it's almost like a cone, right? It's a cone. There's a formula for a cone. It's 1/3 pi r squared. But it's like you're taking that and you're cutting off the top piece and you're just left with this bottom piece. And so you're trying to find the volume of that. Oh, I need to give you the height, sorry. So the height of this. So can we come up with a formula? So I usually give a bonus. I'm not going to, but can someone come up with an idea of how you can do this?
Wouldn't it just be a linear?
Yeah, this is just a line wrapped around the x-axis, right? Turn your head sideways and look at it like that. And it's a line wrapped around the x-axis, right? So if we wanted to do this, we would just say, okay, I have this line that's wrapped around the x-axis. It goes like this, right? And if I wrap that around the x-axis, I get that object. You'll see it's sideways, but that's what I would get. Now you'd still have to figure out what it is, because you need to know what this is, right? As a function, y equals what? But what do you know? Could you come up with a function for this line? Can someone tell me what this point is right here? As a point though, as an x and y coordinate. You're on the right track. 0, R1. Yeah, that's 0, R1, isn't it? That's what it is. Okay, what's this point? Not 0, not 0, but R2 I agree with. R2 I agree with, because that's distance from here to here. What's the distance from here to here? We called it h in the picture, right? The height of this would be h, right? And if you know 2 points, can you find the equation of a line through 2 points? Once you find that equation, you've got your function. And then you're just going to integrate pi times the integral from where to where? This would be pi integral from where are we starting? 0, where are we stopping? H. And we're integrating this line, which is still a question. We still need to figure out what that line is, right? But it'd be whatever that line is, squared dx. Because the outer radius is the top edge, and the inner radius is 0. See? You could, so if you wanted, you could take this a step backwards. If you wanted to prove that the volume of a cone, right, is 1/3 pi r squared, you could do this the same way. What's the big difference between this and a cone though? Where does the cone start at? At the origin, then it goes up like this, right? And so this right here, right, this point would be the height of the cone, r, because in a cone, we only have one radius, the bottom. We don't have an R1 and R2. And then this is the point 0, 0, isn't it? And because of that, we actually can come up with that equation easily. That's y equals, let's see, we have the y-intercept is 0, right? Do we have a slope? Rise, run. What's the rise? R, run, h. This is r over h, x. That's the equation of that line. I know I'm moving fast here, but I could set this integral up, pi integral 0 to h of r over h x, that squared dx. It's the outer radius squared. Okay, I'll let you, you can do that yourself. But so to answer your question, like pretty much anything you can think of that has some symmetry when you know, as a volume, as a solid, you can use the integral. But see, the integral is even more powerful than that. It can, there's applications that we can get to later, like if you wanted to know, let's say you had a tank and that tank was filled with water, and you wanted to pump that water up and out of this tank, and you wanted to know how much energy or work needed to be done to pump that water out of that tank. What you do is you figure out, you cut this, now we're going way past where we are today, but what you do is you imagine that this water is made up of an infinite number of layers like this. And so what you're trying to do is figure out how much energy or work is required to take one layer and move it up and out. So you have to work against gravity, and you know, the further down you are, the more you have to go up and out. So, but it's the same concept. You divide it up into these infinite number of things and then add them all up. And the integral is the tool for that. So,
Depends also the power of the pump, right?
well, that might determine the time it takes, but work is, you know, force times distance pretty much. So whatever force is required to move something over a distance will give you the work. Okay, we're going beyond. I just really want you all to have some proper respect for what the integral really is. And it gives us this wonderful tool to do tremendous amount of things with. All right, let's do one example on your own, just to make sure you understand the mechanics of this. Nothing fancy. Let's take, let's see, I want you to find the volume of solid formed by rotating region bounded by y equals x squared and y equals x, not x squared, 4 minus x squared about the x-axis. This is just so you can see like what these problems look like when they're formulated like on a test. Like this is the way it's presented to you. So find the volume of the solid formed by rotating the region bounded by those two graphs about the x-axis. You want to try it? Okay, go for it. You're going to need pictures. Pictures, look, you know how I was doing the rectangle, moving it to the side and labeling all that stuff? There's a reason I did that. It will be very helpful if you can do that too, because after this problem, we're going to start moving the axis of rotation. So the pictures are going to matter. All right, go for it. Aaron, I got your chat there. I will try, just remind me at the end. It's going to help a lot to know what the graphs of these things look like. I'm going to start working this. So maybe you can take a look just to make sure you're kind of on the same track here. If you've gotten to the point where you've set the integral up, just pause at that, okay? Because that integral we can do whenever, you know? Most important thing is the setup of the integral. So I drew the functions x squared, 4 minus x squared. I saw the region between them, realized I was going to need to figure out where these two intersect one another. So I set them equal to each other and got two solutions, plus or minus root 2. I drew the rectangle to the side. I drew my x-axis, my axis of rotation, figured out what the inner radius is, figured out what the outer radius is, and that is plugged into the formula. Pi integral a to b, outer radius squared minus inner radius squared, and then I just crank this out. Does that make sense, everyone? Does anyone need help with this? On your next test, I think I told you all this last time, on your next test, I will ask you to find the area between two curves, and I want you to give me the answer. But when it comes to the volumes, I'm just going to have you set up the integrals. So you're not going to actually take this the rest of the way. You're just going to set it up and be done. All right? Because it'll take too long for us to have to continually have to take these and do all the mechanical integration. Yep. I mean, today I wanted you to get a numerical answer, but we'll just stop here. Okay? Any questions? You sure? We're about to move on to do something a little different. We're going to do the same exact problem, but we're going to do something different. You ready? So let's take this new problem. Whoa, uh-oh. The computer's freaking out. There we go. It's acting weird. Okay, here's what I want us to do. Find the volume of the solid formed by rotating the region bounded by these two curves. So same two curves, but not about the x-axis. I want you to rotate it about y equals -4. So where is y equals -4? What is it? What is y equals -4? It's a straight line, horizontal line, right? Down at -4. So watch me work this out. I'm going to draw my x and y axes over here. I have a parabola that opens up. Y equals x squared. I have a parabola that opens down. Y equals 4 minus x squared. But my axis of rotation is down here at y equals -4. Now, do you agree that we should get a different volume than we do when we wrap around the x-axis? Do y'all understand that because originally this region was just going to, in the previous problem, it just went around the x-axis, which means we're going to have this small weird shaped solid, right? Almost like a donut. But if we wrap this around the x-axis, there will be no hole in the donut, right? But if we wrap it around this line, it's got to come all the way around and back through, right? And you're going to have a huge hole in it. So it's going to be taking up much more space. And so it's going to have a different volume. Understand? So this is where the drawing is so important. Watch. I'm going to put my rectangle in here. And now I'm going to slide everything to the side. So here's my x-axis. Here's my rectangle. Right? I'm going to zoom in just a little bit on this. There's my rectangle. And then my axis of rotation is down here. Right? That's my axis of rotation. With me? Let me label R out first. R out is the distance from the axis of rotation all the way to the top edge of that rectangle. This is R out. Let me say that again. R out is the distance from the axis of rotation to the outer edge. I like to imagine it this way. If you were a person standing here, imagine that's looking from the top down, that's your head, right? And if you imagine if you were looking out and you wanted to measure how far from you to the outer edge of that rectangle, right? That's the distance that we're looking for. That's R out. R in is the distance from you to the inner edge of the rectangle. This would be R in. The distance from the axis of rotation to the outer edge of the rectangle is R out. The distance from the axis of rotation to the inner edge of the rectangle is R in. And do y'all see that R out and R in are not the two functions anymore? Do y'all see that? Because look at the top of this, the top part of this rectangle. It's dictated by the green function, right? But the green function only gives you the distance from here to here, right? From the x-axis to there. That's 4 minus x squared. And then the bottom edge from here to here, that's x squared, right? That's not what we're looking for though. 4 minus x squared is not my R out, and x squared is not my R in. What's R out? We have to include this distance, don't we? Which is what? -4, but we're going to look at it like a distance. So we're just going to say 4. And then from here to here also is 4, isn't it? So R out is 4 plus that much, right? And R in is 4 plus that much. Once you have it established, everything else is just the formula. So the volume will be pi Same limits of integration, negative root 2 to root 2. But now you're going to have r out squared minus r in squared dx. So what did we say r out was? 4 plus the 4 minus x squared, right? And then the other one was 4 plus x squared. And you could do this, right? I mean, if you were given enough time here, you could do this. You just like put these two together. It's 8 minus x squared. You square that. You do 4 plus x squared. You square that. So you'd have to like FOIL or expand or whatever. You get this polynomial function. You could integrate term by term. It'd be ugly. I mean, it'd be nasty, like, you know, plugging root 2 in would suck, but we could do it, right? See, so this is the part where in reality, right, in the real world, we would go to a computer now, right? The computer is not going to set the integral up for us, though. And that's what it's like. The real world, you have an engineering problem, right? You want to get the math to do it. Once you get to the math, then you can use software to do it, right? But the computer is not going to take this input and be able to generate the integral for you. Yeah, exactly. Put it together. Yeah. We'll use the technology when we need it. Like right now, if I ask you, what's 375 times 267, right? You're going to go to your calculator. Why? Because it makes the most sense, right? I mean, could you do it by hand? Sure. So we actually get to a point in engineering where it's like, okay, you just have to get the problem from the real world to the math. Then we use the computer to do it, right? Okay. Now, you ready? Same problem. We're going to rotate it around something else. I should just say right now, so you know, we will only ever rotate around horizontal and vertical lines in here. There is a way to rotate around lines that are slanted, but it's beyond the scope of this class. All right. No, it's beyond the Cal 3 too. It's very difficult to do. In general, it's hard to do. Because in order to do what we're doing, right, we need a function of x so that our rectangles are vertical. If we want to go around this way, we would need functions of y to turn our, but if we do it around some arbitrary line, we may not have a function of x or y because things start getting slanted over and it just becomes a mess. So there's a way to do it. It's not simple. In what? Like needing a slant? As far as application, really, it's not necessarily that you would need to find the volume of something over some weird line. It's, do we have a way of taking all the math that we have and doing it rotated? That's more profound. And then that has bigger implications because in the real world, things just don't always line up the way we want them to. They're not always going to be looking at a function of x or a function of y. But if we tilt our head, maybe it does look like a function of x or y. But so how do you tilt your head in the real world, right? So we need these transformations where you can rotate the entire xy plane. And so how does that change the math? It turns out to just be a matrix. Like you just multiply everything by matrices and it rotates it. It's weird, but you need to know linear algebra. And so it's very applicable. But here we're just limiting ourselves horizontal and vertical lines. Okay, so here we go. I'm going to change this. Ready? I want us to rotate this around, not y equals -4. Let's go y equals 7. So where's this axis of rotation now? Above the whole region, right? In the previous problem that we did, well, let's go back. The original problem, let's look at the original problem. The original problem, we rotated this region around the x-axis, right? Then we rotated that region around a line that was below, right? And now we're going to rotate around a line that is above it. We will never rotate around a line that goes through it because then what you wind up doing is getting a double volume, and it doesn't make a lot of sense. So we'll always be either below or above or right on it, right on the edge. Okay, so here we go. So I start with the picture again, okay? And I draw my parabola x squared, here it is. I draw my other parabola, 4 minus, I'm going to move it down a little bit like this, so it'll be 4 minus x squared. And then now my very important axis of rotation, which is up here at 7. I'm trying to get that region and rotate that around that. So I get my rectangle. And now I'm going to draw things out to the side. X-axis. Rectangle. The green function is on top. The blue one's on the bottom. My axis of rotation's up here. And now I need to figure out what R out is. So Bree, I said R out was what? You asked me to repeat it. It was R out is the distance from the axis of rotation to the outer edge of the rectangle. So pay attention. You're standing on the axis of rotation. See my head? And I'm looking out to the outer edge of the rectangle, which is no longer this top one. It's now that, isn't it? Isn't that R out for me? I'm physically standing here and I'm looking to the outer edge of the rectangle, which is now this bottom edge. And R in is this one. Y'all see that? Do you see how having that line above changes things? Now, the things that we do know is we know the distance from the x-axis to that top edge is 4 minus x squared, bless you. And we know that the distance from the x-axis to the bottom edge, we know that's x squared, right? So any questions on that picture? X-axis to bottom edge is x squared. X-axis to top edge is 4 minus x squared. But we want this distance and this distance. So there's one more distance we know. We know the distance from here all the way down is what? 7. So what would this be? R out. 7 minus x squared. So this distance is x squared, right? This distance would be take 7 and take away that x squared. So R out is 7 minus x squared. What would R in be? Seven minus the 4 minus x squared. That has to be in parentheses on the 4 minus x squared. So it's the entire distance, 7, take away this much. Understand? So we have R out, we have R in. Formula. Cruz, you all right or no? Sure, you got it? Okay. So the volume is pi integral negative root 2 to root 2. We have the outer radius squared minus the inner radius squared dx. The outer radius is 7 minus x squared, and the inner radius is 7 minus 4 minus x squared. And that's it. Whatever that integral is the volume. So this is what I normally do on a test. I'll give you something like this, where I give you a question like this in the beginning. First thing I'll ask you to do is find the area between the two. Okay? That's 7.1. Then I'll ask you to find the volume if you rotate it around the x-axis. And I'll say, find the volume if you rotate it around a line below it, like x equals -4, or sorry, y equals -4. Then I'll say, okay, find the volume if you rotate around a line above it, like y equals 7. But for all the volume ones, I say just set up the integral, okay? The first part area, I'll actually have you do that. But it'll be the same region through all the problems. That way you don't have to like rethink through the region. So it's important you get it right that first time, because if it's wrong the first time, It's off. The whole, everything's off. Okay. All right, questions. All right, so we've done the x-axis, we've done a line below it, a line above it. What do we, yeah, we haven't done vertical lines yet, have we? Okay, so let's go back and let's do the problem we started this whole thing with. Let's go back to the sine function between 0 and pi. I want us to just think about this again. So if we were to take y equals sine x on the interval 0 to pi and above the x-axis, that's the picture we started class with. It looked like this. We know how to take that region and we know how to wrap it around the x-axis, right? We could actually do that. We could wrap it around the x-axis. We could wrap it around a line below it or above it, right? I didn't ask you to do that, but we could now. Because we see the rectangles, right? So we could figure out what the R out and R in are. But what about if we try the y-axis? What if we try and wrap it around the y-axis? What fundamentally do you see as an issue here? What's, yeah, so your rectangle, right? What would your rectangle look like? Could you do a vertical? If you wrap that around the y-axis, if I try and wrap that around the y-axis, do you get the washer that we had before? Not really. I mean, kind of, but not really. Yeah, it's really kind of why it would look strange, wouldn't it? I mean, around the x-axis, it's definitely a washer. But around the y-axis, but what about turning the rectangle sideways? Could we do that? Maybe if we turn it sideways like this, now it's more like the washers method. You see that? But what's wrong with that? Same function, right? The sine function is not a function that way because the right edge and the left edge are the same curve, right? So you can't do that. So how do we do it? Well, we have to come up with a new formula. Okay, we need a new formula. The formula we've been using is volume equals pi integral from a to b of outer radius squared minus inner radius squared dx, right? That's the formula we've been doing. Instead of that formula, we're going to generate a new one. So here's how it's going to work. We're going to start it with this to see if I can't motivate the idea here. So what if we take that vertical rectangle, which we can do, right? And let's wrap it around the y-axis. Let's wrap it, okay? If we wrap it, what it's going to look like is, what does that look like? It looks like this, doesn't it? If we wrap that around the y-axis, a rectangle around the y-axis, it should look like this. Can you visualize that? That rectangle wrapped this way? That is not what we call a washer in here. What we're going to call this is a shell. Okay, it's a shell. Why? Shell. This object, shell. S-H-E-L-L, shell. Okay. So you know how when we were doing this, we said, oh, when we have this washer, we could come up with a formula. All we needed to know was the inner radius and outer radius. And then we just came up with that formula and nobody argued with me. Everyone agreed that that was the formula. We need to come up with a formula like we did with this for that shell. Okay, so I need to work on this. Maybe we can go back to this. If I take that and wrap it around, let me try and draw this shell. It's gonna be really tall. That. It's going to have like a thickness to it like this. And my question is, can I find a volume of this? A volume for this? Well, how tall is it? F of x, right? Isn't that just the height of the function? So as I move this, if I move the rectangle to the left a little bit, it's going to get smaller, but that'll make this, not as tall, right? So that is all being dictated by the function. I agree with that. This distance from here to here should be f of x. But what the heck, man? How are we going to find the volume? What? Right? This seems weird, right? How to find the volume of this, because it's hollow on the inside. So I'm going to do something strange here. I'm going to take some scissors and I'm going to cut this. Okay? I'm going to cut it. I'm going to lay it flat. All right? If I cut that open and lay it flat, it now looks like this. Right? Basically. This is still f of x. But now, do y'all see that we have a parallelepiped, a box? To find the volume, we just need length times width times height. Can y'all tell me how thick this little piece is? Dx, right? Because that came from the width of the rectangle, right? Is what dictates how thick this thing is. So this is dx. So what's the only thing left for us to figure out? How long it is, right? How long is this? Here's our shell, right? We cut it open. This distance from here to here is the circumference of the circle, right? It's the circumference of the circle. What's the formula for circumference? Circumference is 2 pi r, isn't it? 2 pi r. So this is circumference, which is 2 pi times the radius. But hold on, radius of what? Radius, we're talking radius is the distance from here to here, right? Right? That's the distance from here to here. What is that in our picture? Drum roll. X. Excellent. Yes. The distance from here to here is x, but that's also the radius. If we rotate this around the y-axis, right? Then that rotation, that radius is the r, is the x. I told you all we're going to need this. This is why I was telling you that. Of course, if you change x, that's going to change how far out you are, right? And that's going to change how wide your shell is. Understand? So what is the volume of this thing? Let me write the formula. The volume of this one thing is 2 pi, but not x. I mean, not r, right? X times f of x times dx. That's the volume of that one piece. 2 pi x gives you this length. F of x gives you the height, and d of x gives you the thickness. Multiply all three together, and you get the volume of that one little slab. And now we use the integral to add them up. Understand? Now, when we do our integral is going to go from, well, let me see. I can pull a 2 pi out, can't I? Because this 2 pi is a constant. Then I'm going to have x times f of x, and then dx. What about my limits of integration? Well, that's going to be our restrictions on x, right? So from the far left to the far right. So x will start out here in this particular example at 0 and end at pi, right? Generally speaking, though, it would be a to b, right? We're starting to see kind of how we're going to form it. Don't box this up. This is not our final formula. This is like the most basic version of it. 2 pi comes from the idea that we're going to have a circumference. X comes from the idea that we have a distance from our rectangle to our axis of rotation where we're rotating. And then f of x is the height of it, and d of x is the thickness. Go with me. I only have 9 minutes. Let me see if I can get to like a final formula. All right. So shells. Here's how we're going to do it. I'm gonna draw an arbitrary picture. Call that function f. Call this function g. I'm going to take a rectangle in here like this. And I'm going to imagine wrapping it around, right? Wrapping it around, not the y-axis, any vertical line, okay? Any vertical line. So when I draw this vertical line, I'm not going to put it on the y-axis. I'm just going to put it here. Keep in mind, this line could be the y-axis. It could be to the left of the y-axis. It could be over here, okay? Doesn't matter where it is. It's just vertical. So when I wrap this thing around, right? When I wrap that thing around, I get this shell. What's the height of it? F of x would be the top of it. What would, and the bottom of it would be the g, right? So that would be f of x minus g of x, wouldn't it be? Now, earlier today, we didn't even call it f of x and g of x. We called it, didn't we say top minus bottom? That was the top function minus the bottom function, right? That should be the height of this rectangle. Cut the thing open and lay it out flat. Oh, this part's so tricky. Cut it, lay it out flat. Okay, we know how tall it is. Top minus bottom. How thick is it? Still dx. This is the part that's tricky. It's 2 pi times the radius, right? 2 pi times the radius. Y'all okay with that? I need the radius now. What is the radius here in this picture? It is not x. Y'all see that? The radius is actually the distance from here all the way to here. That's our radius, right? The distance from here to here is x, but it doesn't necessarily mean that r is x. If the y-axis is our axis of rotation, then the radius is x. But if it's somewhere else, we're going to have to figure out what it is. So this radius that we're not sure of, okay, because it depends on our axis of rotation, what I'm going to do is in this formula, I'm going to write r, I'm going to write, if it won't lets me, r sub x. And that just means that this radius depends on axis of rotation. So now to get the final kind of version of the formula, the total volume of this should be 2 pi, which I can pull out, integral from a to b. Now, where a and b? Those are where the two things intersect each other, okay? A, b, and then it's going to be whatever the radius is times the top minus the bottom dx. This is our kind of master formula. Now, I only have 5 minutes, but I'd like to see if we can't at least do that sine one, okay? So I really don't know if I have enough time for this. What do y'all think? Should I try and squeeze in or just wait? What do you want to do? Yeah, okay. All right, so what I like for us to do is this. I don't want to write this or type it all out. I want us to take the sine function, right here, from 0 to pi. And for part A, I'm going to rotate about the y-axis. For part B, I want to rotate about x equals -2. And then for part C, I want to rotate it about x equals 2 pi. So let's do part A first. So I look at this and I say, all right, I want to rotate this around the x-axis. Sorry, the y-axis. So I imagine a rectangle here, and I imagine it being rotated around like this, right? It's going to go around. So I know right now that means I'm going to be using shells. One way you can tell if you're using shells is that if your rectangle is parallel to your axis of rotation, then you're using shells. If your rectangles are perpendicular to your axis of rotation, then you're doing washers. You look back at what we've done. Anytime the rectangle was like this and the axis of rotation was this way, then you'd have to use washers. Okay, so to do shells, it's actually pretty simple. You just need to know the top and the bottom function, which we know here, right? Top is sine, bottom is 0. And then you just need to know your Rx, this distance from here to here, from the axis of rotation to the rectangle, which for this example is what? It's just x. So this should be 2 pi integral 0 to pi x top function minus bottom function dx. Done. That's the integral. How would you integrate that? X sine x. Integration by parts. Do I need to explain this? Let's do part B. Rotate it around x equals -2. So if I think about this picture, here it is. Got my rectangle. X equals -2 is over here. This is my axis of rotation. I'm parallel to my rectangle, so I know when I wrap this around, it's going to be shells. So my volume should be 2 pi integral 0 to pi. What's my radius? So look at it as a distance again. This is almost like an absolute value. What's the distance from here to here? 2. And then distance from here to here? X. Add them up. So your radius is 2 plus x, or x plus 2. And then top minus bottom. dx. That makes sense? Last one. Want to rotate it around 2 pi. Leave that right there. So to go around 2 pi, x equals 2 pi. Here's my picture. Here's my sine curve. 2 pi is out here, isn't it? My rectangle's here. Look at this though. This is my radius from this axis of rotation to the rectangle, right? Now we know this distance from here to here is x, right? And the whole distance is what? 2 pi. So this distance should be 2 pi take away x. So my volume should be 2 pi integral 0 to pi 2 pi minus x top minus bottom dx. Done. All right, I hope that makes sense. We're out of time. You're going to want to do your homework for 7-2. Okay, but I'll just warn you right now, something in 7.2 that did not come up here is what if you had something that looked like this? Y'all can pack up. What if you had something that looks like this? And you wanted to rotate it this way around the y-axis. It would be like a washer, but everything's going to be with respect to y. So you can only draw your rectangles this way, right? Because it's not a function of x. These are functions of y. So your formula would basically be the same, except you'd go C to D here. Because this would be washers, you would be doing volume equals pi, not 2 pi, that's shells. You go from C to D, then you'd go R out squared minus R in squared dy. And the outer and inner radius would be distances from your axis of rotation here and here. See that difference? It's just everything sideways. See how it goes. I'm hoping you'll come to me with some questions next class. Okay, the chat, someone wanted me to talk about problem 6. You're free to go if you'd like. I'm gonna put up here problem 6 solutions for the exam. All right, so for problem number 6, it's a partial fractions. So you have to first do long division, which would be this over here, which gives you a remainder of negative x squared minus 18. And that goes on top of this. And then you have your 1 from here. So then you have to figure out what this is. And for that, the denominator factors. And then from there, you can do your partial fractions on this. So because I have a x squared, I can do a over x plus b over x squared. And then because x squared plus 9 is not reducible, I have to put a linear on top of it. And then I go figure out what a, b, and c are. A, b, c, and d are. So Aaron, I don't know if have I gotten to a point where is this clarifying things or?
Yeah, that's great.
Okay.
Let me see.
Yeah, once you find out what A, B, C, and D are, then you just replace them. And it turns out to be the first one is just going to turn out to be a power rule. And the second one we should recognize is the antiderivative is arctan. Oops. And yeah, there it is. Do I need to go through anything else on that?
No, that's it. Thank you.
Okay.
Can I see that last integral from C on the lecture today?
Yes. There we go. What you got, Christian?
Okay, thank you. Bye.
Okay, no problem. Take care, Aaron.